Welcome to the Deep Dive, where we sift through mountains of research, so you don't have to. Today, we're taking a look at the evolution of computational phantoms. You know, those digital stand-ins for the human body, the ones that are essential in medical physics.
And they've become especially fascinating now in the era of AI and just, ever-increasing computing power.
Yeah. You're right. Those are the real game changers, the things that are really pushing the field forward. But before we get too deep into that, I want to make sure everyone's on the same page. For folks who might be new to this, can you give us just a quick rundown of what computational phantoms are and why they matter in medical physics?
Sure. At their core, computational phantoms are digital representations of the human body, and they're built using mathematical models, anatomical data, and they're critical for radiation dosimetry, which is all about, calculating how much radiation energy is deposited in different tissues.
The organs.
So instead of experimenting on actual people, we can use these virtual humans to estimate radiation doses in a variety of different scenarios, right? Exactly. That's why they're indispensable in fields like medical imaging, radiation therapy, and radiation protection. It's all about ensuring safety and effectiveness when you're working with radiation.
Okay. Makes sense. Now, I know that these phantoms have gone through several major transformations. As computing technology has advanced, it's like they've evolved alongside our digital capabilities. Where did it all begin?
Well, the earliest computational phantoms, developed back in the 1960s and 70s, were known as stylized phantoms, and they were incredibly simple by today's standards.
Simple how? Paint us a picture of these early models.
Imagine basic geometric shapes, like cylinders, cones, and spheres, cobbled together to just, roughly approximate the human form. The famous MIRD5 phantom is a classic example. It was based on the concept of reference man, sort of this average adult male figure.
Yeah. I remember seeing pictures of those early phantoms. It almost looked like something out of a retro video game, all blocky and pixelated. I can't imagine they were all that accurate.
You're right. They were pretty basic. Some even lacked details like fingers, noses, or chins. But considering the limited computing power at the time, they were a remarkable achievement. They did lay the foundation for, everything that came after.
I'm curious how they accounted for the differences between men, women, and children with these early models. Did they just scale the reference man up or down?
That's a good question. Researchers at Oak Ridge National Laboratory actually created a family of stylized phantoms to address that. They developed models for newborns, children of various ages, and even a pregnant woman, all variations on that basic MRD5 design.
So they were starting to recognize the need for more diverse representations even back then. But I'm guessing those stylized phantoms had their limitations.
Oh, absolutely. Their biggest drawback was their lack of anatomical realism. Trying to represent complex organs with simple geometric shapes inevitably led to inaccuracies in dose calculations. And of course, they were completely static. No movement, no flexibility, no way to simulate the dynamic nature of a real body.
So it was like trying to fit square pegs into round holes. Not ideal when you're dealing with something as sensitive as radiation. What happened next? Did the evolution of phantoms just stall out there?
Not at all. In the 1980s, the arrival of CT and MRI, that revolutionized medical imaging. And that had a huge impact on phantom development. We entered the age of voxel phantoms.
Voxel phantoms. Those are the ones built from 3D grids of tiny cubes. Right? Each cube representing a different tissue type and density.
Exactly. Think of it like digitizing the human body. Suddenly, we could incorporate far more anatomical detail into our phantoms thanks to these high-resolution images.
That must have been a game changer for accuracy.
It was. A research team led by Zankel, they really pioneered this development, creating a series of 12 voxel phantoms. They had models for babies, children, and adults. Even specific individuals like RX and Regina.
So we were moving away from the generic reference man and towards representations of, actual people. That seems like a huge step towards personalization.
You're right. It opened up a whole new world and possibilities. Take the VIP man phantom, for example. Developed at RPI. It was actually built from color photographs of a cadaver.
Wow, they use actual photographs. That's incredible. How much detail were they able to capture with that method?
Enough to define even very small tissues. And remember the concept of a digital human we talked about earlier. Researchers like Zhu saw these increasingly realistic phantoms as having applications far beyond just radiation dosimetry.
You mean using them to simulate all sorts of biological processes?
Exactly. And it's not hard to see why. The more realistic and detailed these phantoms become, the more potential they have to revolutionize our understanding of the human body.
Okay. So voxel phantoms were a big leap forward, but I'm guessing they weren't the end of the story.
You're right. Even with all that detail, voxel phantoms had their limitations. For one, they were still fairly rigid. You couldn't easily adjust their posture or simulate movement, and the resolution of those voxels, those tiny cubes, still posed a problem.
What kind of problem?
It limited how accurately we could model very thin structures in the body, like the lining of the stomach, or blood vessels. Think of it like trying to recreate a high-definition image with those chunky Lego blocks. You can only get so much detail.
So the quest for even greater realism and accuracy continued.
It did. And that brings us to the next generation of computational phantoms. The BREP phantoms.
Okay, let's unpack that. What does BREP stand for?
Boundary representation. These phantoms, which started emerging in the early 2000s, use advanced mathematical techniques to define organ surfaces with much greater precision. Instead of those blocky voxels, they rely on things like NURBS and polygon meshes.
Those sound like terms I'd hear in a computer graphics class. What's the advantage of using those techniques?
Well, they allow for much finer detail. And importantly, they introduce deformability. Think of it like sculpting the human form in the digital world.
So finally we have phantoms that can move and bend. More like a real person.
Exactly. And that opened up a whole new realm of possibilities. One of the most notable examples is the NURBS-based NCCAT phantom. It was developed from the visible human CT dataset and later extended to 4D to simulate cardiac and respiratory motion.
That's impressive. Now, we're not just talking about a static representation of the body, but one that can actually mimic its dynamic functions.
Right. And the innovations didn't stop there. The RPI team developed a whole range of BRP phantoms, including models for specific postures like walking and sitting, and even models representing different weight percentiles.
So we're getting closer and closer to truly personalized phantoms, tailored to individual body types and movements. That's pretty exciting. But I'm guessing even these advanced BRP phantoms had their challenges.
You're always going to have challenges when you're pushing the boundaries of technology. One of the early hurdles with BRP phantoms was compatibility with existing Monte Carlo codes, which are essential for accurate radiation dose calculations.
So the software needed to catch up with the increasingly sophisticated hardware, so to speak.
Exactly. Plus, some of those early BRP phantoms, particularly the ones using polygon meshes, were computationally demanding and slow. But researchers found a clever solution. Tetrahedral mesh phantoms.
Tetrahedral mesh. That sounds even more complex than polygon mesh. What's the difference?
Instead of representing organs as complex surfaces with numerous polygons, they used a network of simple tetrahedrons, which are basically triangular pyramids. This simplified the geometry without sacrificing accuracy, making them much faster to work with in Monte Carlo simulations.
So it's about finding that sweet spot between realism and computational efficiency.
Exactly. And the ICRP, the International Commission on Radiological Protection, recognized the value of this approach. They developed what they call MRCPs, or mesh-type reference computational phantoms. These are highly detailed, deformable, tetrahedral mesh phantoms that have become the new standard for radiation dosimetry.
That's a testament to how far we've come in just a few decades. We've gone from those blocky, stylized phantoms to these incredibly sophisticated and dynamic models. It's amazing to see how technology has driven this evolution.
It has. But the story doesn't end there. In fact, things are about to get even more interesting as we enter the age of AI and personalized medicine.
That's what I was just thinking. We've laid the groundwork with these increasingly realistic phantoms. But the real game changer is how AI is transforming their development and application. I'm eager to hear more about that.
Me too.
We trace this fascinating evolution from those blocky first-generation models all the way to the incredibly detailed and deformable BREP phantoms. But now AI is taking center stage, and I'm really eager to understand how it's changing the game.
Well, one of the biggest impacts of AI has been in the area of person-specific phantoms. Imagine being able to generate a virtual replica of your own body for truly personalized radiation dosimetry.
That does sound futuristic, but how exactly is AI making that possible? Is it just a matter of, feeding more data into these models?
It's more nuanced than that. AI, specifically deep learning algorithms, excels at a process called auto-segmentation. This involves automatically identifying and outlining organs and tissues in medical images.
So instead of a medical physicist meticulously tracing every organ in a CT scan by hand, AI can do it in a fraction of the time.
Exactly. And that's been a major bottleneck in creating these person-specific phantoms. It used to be incredibly time-consuming and labor-intensive, but AI has made it significantly faster and more efficient.
Yeah, that's a game changer. What kind of software are we talking about here? Are there specific programs that are being used for this?
Yes, there are. One example is Deep Viewer. It can automatically segment organs from CT images in minutes, laying the groundwork for personalized dosimetry in clinical practice.
That's incredible. So we're on the verge of having personalized phantoms for every patient.
We're getting closer. But it's important to remember that AI is a tool. And like any tool, it has its limitations. These AI models need to be trained on vast amounts of high-quality data, and the appearance of organs can vary considerably from person to person due to factors like disease or even how the images were acquired.
So there's still a need for human oversight. We can't just let the AI run wild.
Absolutely not. Clinicians still need to be involved to ensure accuracy and patient safety. They need to check the AI's work, make adjustments if necessary, and ultimately be responsible for the decisions made based on those models.
That makes sense. It's a powerful technology, but it's not a replacement for human expertise and judgment.
Precisely. And that brings us to another key area where AI is making a big impact, speeding up those complex Monte Carlo simulations we talked about earlier.
Yes. Those simulations that track the paths of countless individual radiation particles as they interact with the virtual tissues and organs in a phantom. Incredibly accurate, but notoriously time-consuming.
Right. But AI, coupled with another technological advancement, is changing that.
What's the other piece of the puzzle?
GPUs, or graphics processing units, originally designed for, gaming. They offer massive parallel processing power, making them ideal for handling these complex simulations.
So we've got gaming technology to thank for accelerating radiation dose calculations. That's an interesting connection.
It is, and it's been a real game changer. The Archer code developed at RPI is a great example. It's a GPU-based Monte Carlo code that can perform CT organ dose calculations in near real time.
Near real time. So we're talking about a significant speed increase compared to traditional methods.
Oh, absolutely. And that has major implications for clinical practice. It means we can get faster, more accurate dose estimates, which can help us make more informed decisions about imaging protocols and treatment planning.
It sounds like we're entering a new era of radiation dosimetry, one where AI and GPUs are working together to enhance both speed and precision.
We are. And it's not just about theoretical advancements. Researchers are already putting these tools to use in some really exciting ways. For instance, there's Lou's work demonstrating the significant speed increase achieved using Archer for CT imaging dose calculations compared to traditional CPU-based methods.
So faster dose estimates for CT scans, what are the implications of that for patients?
Well, it could lead to more personalized imaging protocols. Instead of using a one-size-fits-all approach, we could tailor the amount of radiation used in a CT scan to the individual patient, minimizing their exposure while still getting the diagnostic information we need.
That makes sense. What are the researchers catching your eye?
There's Sue's research on using Archer for external beam radiation therapy. Dose verification.
Dose verification. Is that about double-checking the dose calculations used in cancer treatment?
Exactly. It's about making sure that we're delivering the right dose to the tumor while minimizing damage to healthy tissues. Again, GPUs have made this process much, much faster and more efficient.
That's a huge win for cancer patients. Are there any other examples that stand out?
Yes. Peng's work is particularly interesting. They combined machine learning-based segmentation with fast Monte Carlo calculations to perform person-specific CT organ dosimetry.
So taking advantage of both AI for segmentation and GPUs for those speedy calculations.
Exactly. It's a great example of how these technologies can work together to advance the field. And then there's Key's research on developing a whole-body organ dose database for radiotherapy patients using AI segmentation and Archer. This kind of database could be incredibly valuable for assessing the long-term risks of radiation exposure and improving treatment planning.
This is all really fascinating stuff. It seems like we've come a long way from those simple stylized phantoms to these incredibly complex and powerful models.
Yeah.
Where do you see this field going in the next 5 or 10 years? What's on the horizon?
Well, one thing is for sure. The evolution of computational phantoms is far from over. I think we're going to see even greater personalization, with phantoms that not only reflect a person's physical anatomy, but also their unique genetic makeup and physiological characteristics.
They're moving beyond just structure.
Yeah.
Getting into function as well.
Exactly. And this will open up a whole new world of possibilities for personalized medicine. Imagine being able to simulate how a particular drug might affect someone based on their specific genes, or predict their risk of developing certain diseases.
It sounds like science fiction, but based on what we've discussed today, it's not as far-fetched as it might seem. What are some of the challenges that need to be addressed to make this vision a reality?
One of the biggest challenges is data. We need vast amounts of high-quality data to train these AI models and create these personalized phantoms, and that data needs to be diverse, representing a wide range of populations and conditions.
It makes sense. We can't just train these models on a narrow slice of humanity and expect them to work for everyone. What else?
Computational power is another hurdle. These personalized models are going to be incredibly complex and computationally demanding. We're going to need even more powerful computers.
Right.
And more efficient algorithms to handle the sheer volume of data and processing required. And access to those resources isn't always equal. Not every research group or hospital has the latest and greatest technology.
So there's a risk of widening the gap between those who have access to these advanced tools and those who don't.
That's right. And that's something we need to be mindful of as we move forward. We need to ensure that these advancements are accessible to everyone, not just a privileged few.
Absolutely. Access and equity are crucial considerations, especially when we're talking about healthcare technologies. Any other challenges that come to mind?
Well, validation is always an ongoing concern. Just because a phantom is sophisticated and looks realistic doesn't necessarily mean it accurately reflects real human biology. We need rigorous methods for validating these models, comparing their predictions to experimental data from real patients. And that takes time, effort, and resources.
So it's a constant process of refinement and improvement. We can't just build a fancy model and call it a day.
Exactly. We need to constantly be testing and tweaking these phantoms to ensure they're as accurate and reliable as possible. After all, we're talking about tools that could have a major impact on people's lives. We need to be confident that they're up to the task.
Well said. I think that's a great note to end on. It's been an incredibly insightful conversation. Thank you for taking us on this deep dive into the world of computational phantoms. It's clear that we're on the cusp of some truly remarkable advancements in this field with the potential to transform healthcare as we know it.
The pleasure was all mine. And I want to add one final thought. It's easy to get caught up in the technology and the amazing things we can do with these phantoms. But at the end of the day, it's all about improving human health and well-being. That's what drives me and countless other researchers in this field.
Well said. To our listeners, thank you for joining us on the deep dive. We hope you found this exploration of computational phantoms as fascinating as we did. Until next time, keep exploring, keep learning, and keep diving deep.